Free body diagram questions for a block on an inclined plane. Redrawing it out such that I place the block higher up on the inclined plane, not necessarily to make the problem more descriptive, but rather to give me more real estate to work with when building my free body diagrams. Accounting for all forces that are acting on my block, initially I have a force of gravity, which is exerted straight down. Next, I have a normal force that is traveling perpendicular to the surface on which I'm on, realizing that this normal force, as represented by this vector here, can easily be transposed right here, thus building a new right triangle. This is that normal force vector here. This new triangle that I have has either reference angle here of 20 degrees or here of 70 degrees. Depending on how you learn how to deal with block on inclined plane problems, you can use either reference angle. I prefer to use reference angle 70 degrees in order to solve for the other two forces that are always acting on blocks in an inclined plane. My normal force and my force of gravity as applied down that inclined plane, terming that F gap, force of gravity applied down the inclined plane. We can solve for both of those by doing some trigonometry. For example, the F gap, the force of gravity applied down the inclined plane, is equal to my force of gravity. In this case, thinking about my reference triangle and which angle I'm working with here, that is the adjacent side of that triangle. Therefore, we would use cosine. Cosine. I end up with 85.5 newtons for force of gravity applied down the inclined plane. For normal force, thinking about where that's located on the triangle, once again, treating my force of gravity as the hypotenuse for my new reference triangle, the normal force with regards to reference angle 70 would be opposite. This is opposite that. Therefore, the appropriate trig function to use would be sine. Solving for that, I get an appropriate normal force of 235 newtons. Finally, I have a force of friction that is opposing my block's motion and trying to slow us down. Force of friction, usually pretty routine to solve for. In solving for force of friction, we realize that it's equal to our normal force times the coefficient of kinetic friction. Although when you go to plug in those numbers in this particular situation, we know our normal force, 235, we do not know our coefficient of kinetic friction in this particular situation. It's not given. We need to solve for it. It would seem that we're stuck. We're really not. Here's why. We do know what our net force is. I'm going to walk over here and solve for that. Net force is equal to the mass of the object times the net acceleration. Plugging in appropriately for that, we land on the numbers where our net mass right now is equal to 2.5. Our acceleration in this particular situation is equal to 0.6. Our net force is therefore equal to 1.5 newtons. Whenever we're dealing with a block on an inclined plane, all the stuff about force of gravity and normal force is just a means to an end in order to solve for our forces of friction, forces of gravity, or other forces that may be acting parallel to the block's motion. In this case, we have no auxiliary forces to keep track of. Nobody's pushing this block. Nobody's kicking or pulling on this block. So you only have two real forces that we need to worry about. Once again, I wouldn't get rid of normal force of gravity, but when it comes up to summing up everything that's going on, you really have those two forces acting in a tug of war. Therefore, my net force in this particular problem is equal to my force of gravity applied down the inclined plane, which I know wins because this object will fall down the inclined plane, minus the force of kinetic friction. Once again, this is not an equation which I memorized. It logically applies situation specific to this particular problem. Plugging in, I have my net force. I have my force of gravity applied down the inclined plane. I can now solve for my force of friction in this particular scenario. Force of friction I land on is equal to 84 newtons. Now I can walk that down here to this equation that we forgot about just a moment ago on the bottom right of the paper. Force of friction is equal to 84 newtons. Force of normal in this particular scenario is 235. 235. Coefficient of kinetic friction is equal to 84 divided by 235, or 0.36. Coefficients of friction have no units, therefore this is the correct answer.